All right, in the last video we talked about molality. In this video we're going to be talking about an application of it, which is the idea of freezing point depression and boiling point elevation. The basic concept here is that if you have a solvent, it will have a phase diagram. We saw this in a previous video a couple videos ago, hopefully still somewhat fresh in your mind. Okay, and we saw there were some points on here where like where it crosses from solid to liquid at standard temperature, or standard pressure, is your normal melting point. There's going to be a lot on this graph, sorry. Where it crosses from liquid to gas is the normal boiling point. Nothing too weird, nothing we haven't seen already. Going to be abbreviating a lot of stuff here, sorry. Well, it turns out that because of intermolecular forces, to cross things from solid to liquid, what you have to overcome, if it's water, let's say, you have to, this thing will be in a crystal structure, you have to overcome those forces and make it break so that it can be a liquid. And then if you keep heating it, you have to overcome those forces to make it pull apart to become a gas. Okay, solid, liquid, gas. Okay, well, it turns out that if you throw a solvent in there and make it a solution, that increases the amount of intermolecular forces. And it only increases the amount of intermolecular forces in the liquid phase, because the liquid is the thing that's dissolving it. If you have a solid, it won't dissolve right, and if you have a gas, it won't dissolve right. So what it essentially does is it expands the liquid range. Okay, so the black lines are going to be the solvent by itself, which I guess I will label. Okay. If you add a solute to it and make a solution, what's going to happen is you're going to get some of these lines shifting around. So this is the solution. Okay? And what happens is your melting point actually drops and your boiling point actually increases. This is the new melting point. And this is the new boiling point. I'm guessing I probably should have written that up there, but too late now. Okay. So let's talk about what happens as a consequence of this. Like, you guys actually have real world experience with this. Okay. Let's talk about the left side first. This is actually why we throw salt on our steps to get rid of the ice. Is ice typically freezes at 0 degrees Celsius or 32 degrees Fahrenheit, whichever one you're used to. Probably Fahrenheit. Okay. If you add salt, the reason it melts is because you've lowered the melting point. So there is a limit to salt melting the ice on your steps. At some point it just won't work. But for most situations, if you just throw a handful of salt on it or a scoop of it, there's more than enough salt to lower the melting point to be cold enough that basically the temperature you're dealing with will be right in this range, so it'll stay melted. Okay? Similar reason as to why they pour salt on the roads. It doesn't actually have to be salt, it's just anything that dissolves in water. It's considered a colligative property. It doesn't depend on the identity of the material. You could use sugar. Actually, that's pretty common in a lot of cities. I know Cincinnati does this. They actually, instead of pouring salt on the roads because it kind of corrodes the sewer systems, they actually pour beet juice, which is basically just sugar water. And yes, it's kind of red, but it's pretty diluted and it's mixed with salt to kind of balance everything out. And the sugar does the exact same thing. As long as it dissolves in water, your melting point will drop. Okay. Similarly, this also applies to things like cooking. I know growing up that my mom, who is not a chemist, let's put it that way, she used to tell me, oh yeah, if you're boiling water, if you're like making pasta or something, just pour a bunch of salt in there because it'll make it boil faster. Yes and no. I don't know how to do that. I don't know how to do the double quote thing with this, and I had water in my hand. It actually makes it boil slower, sort of. So what happens is the boiling point goes up. So if you take a pot of water, turn it on full blast, a given amount of water, and you had two pots that were next to each other, the same amount of water, same amount of heat, and you poured salt into one of them, the one that doesn't have salt should boil first, okay? But the important part here is once it does get to boiling, it will be boiling at a higher temperature, which allows your pasta to cook faster. So it doesn't make the water boil faster, but it does boil your food faster because it gets to a higher temperature, okay? Both are important, both matter, but you guys probably have real world experience with this. This doesn't matter a whole lot, but it also does change our triple point. The triple point kind of moved around too. Okay, we're ignoring the supercritical fluid aspect of this on this particular phase diagram. I only care about this little distance here. So what we need to do is look at some equations to know, based off how much salt we throw in, based on the concentration, the molality, how much is the temperature going to change? You know, if you throw in like one little speck of table salt versus, you know, half a cup of table salt, how much of a temperature difference are you going to get? Because obviously the temperature is going to go up for the new boiling point, or it's going to go down for the new freezing point, but we want to know how much. Okay, so what we care about for this particular example, I'm looking for a different colored pen, but I guess we're going with blue, is this is our change in melting point. Change in freezing point is usually how it's abbreviated, because we usually visualize this from the liquid phase. You're decreasing the temperature at which it freezes. Freezing point and melting point are the exact same thing. Similarly, there is a change in boiling point, and this is delta TB. We want to know, how do you calculate what those values are going to be? And unfortunately, they're not the same. So we need to look at some equations, and let's see what happens. Okay, so delta TF, this change in freezing point, is equal, it looks like a really simple equation, and it kind of is something called negative KF times M. It's negative because the freezing point is going to drop, okay? So this accounts for that. KF is literally just a constant. So this is, I guess I should label everything, change in freezing point KF is your, it's called the Molal freezing point depression constant. And the units on this are degrees C per molal, not per mole, per molal, because this is molality. Right. Okay, and we've seen molality in the previous video. It's equal to moles of solute per kilogram of solvent. Okay. There is another equation to account for this one, how much the boiling point is going up, and it looks almost identical. Okay, so delta TB equals positive KB times M. So this is the change in boiling point. KB is positive because the boiling point goes up. So there's no need for a negative, okay? This is the molal boiling point elevation constant. And this is also degrees C per molal, and this is still molality, which I'm not going to relabel because it's literally right there. Okay, so this KF and KB value is basically just a constant, and it is only dependent on the solvent. So there are KB values for water that are different for, you know, benzene or ethanol or whatever your solvent might be. Okay. Unfortunately, KF and KB are not the same, and depending on what your solvent is, KB might be bigger than KF or KF might be bigger than KB. But let's try a couple examples just to see how to use this equation to solve for these changes in temperature. Okay. So I guess this is page 5, just so I can keep track. All right, let's just try an example. We want to know, what is the boiling point of a 12.5% weight sodium chloride solution in water? And Kb for water is 0.52 degrees C per molal. Okay, sounds easy enough. So the equation that we care about is we want to know how much does the temperature change. Okay, well, this is Kb times M. Well, we know Kb, M is molality. So the hardest part of these problems, honestly, is solving for molality. So we need to take 12.5% weight of sodium chloride and convert it to molality. So I'm going to do that as a separate kind of thing down here. So this value, 12.5 grams of sodium chloride, if we were solving for molarity, we would say we had 100 grams of solution. We want to know how many grams of water there is. So it'd be 100 minus 12.5, which is 87.5 grams of water. Okay, just like last time, we need this converted to moles, and we need this converted to kilograms. So we're going to have to add up a sodium and a chlorine off the periodic table, and the value comes out to 58.443 grams per mole of sodium chloride. I'm working from a problem I've already done. I'm assuming at this stage of the game that you passed Chem 1, so you can add up things off the periodic table. But that will convert from grams to moles of sodium chloride. To convert from grams to kilograms, just literally have a factor of 1,000. There's 1,000 grams in a kilogram. That will give us moles on top, kilograms on bottom, which will give us a molality of 2.44 molal. Okay. Well, we basically just take that and plug it back into this equation. So to solve for the change in boiling point, we take Kb, which is 0.52 degrees C per molal, times 2.44 molal. You'll note that solving for the molality is the only real hard part of this. Okay. I guess I already have this worked up. I don't know why I was grabbing a calculator. You multiply these together, we get 1.27. I'm fully aware there's only 2 sig figs, but for right now I'm going to wait to round it. Okay, so that would be the second sig fig. So here's the problem. This does not tell us, it asks, what is the boiling point? This is not the answer. This is how much the boiling point changed. So the boiling point is whatever the original boiling point was, plus this new value. So water typically boils at 100.0, and we have increased it by 1.27 degrees Celsius. So the answer is 101 point, I guess I'd round up to 3. So this would be the new boiling point for a 12.5% weight sodium chloride solution. Okay. The reason we have to use molality is because we care about the temperature change, and molarity changes with temperature. Okay. Let's try another one that's a little more difficult. Same type of problem, just kind of asking for something different. Basically, as far as I'm concerned, it's the same thing, but people seem to freak out when I ask them to do these things. So let's try it. So we want to know how many grams of sodium chloride would be needed to lower the freezing point of 50 milliliters of water by 3.00 degrees Celsius. So now we're trying for freezing, but before we had one of those percent weights and we converted it to molality. Okay, what we care about now is we have a certain amount of water and we want the temperature to drop by 3 degrees. How many grams of sodium chloride do we even throw in there? Okay. we need a few numbers here. It turns out that Kf for water is 1.86. In the last problem, we saw that the Kb for water is 0.52. So it turns out that if you throw salt into water, it makes the boiling point change a little bit, but it makes the freezing point change a lot. Okay. We also probably should point out that the density of water, we're just going to run with it being 1.00 grams per milliliter. So we're going to assume that it's a density of 1 because it's water. Water does have a density that varies a little bit as temperature changes, but we're going to ignore that factor right now. So basically, we need to solve for m and then figure out how to solve for that molality. So this equation, delta Tf equals negative Kf times m. Well, delta Tf is basically negative 3 degrees Celsius. It's going to lower it by 3 degrees. Negative Kf is negative 1.86 degrees Celsius per molal. And m is what we're solving for. Okay, these are not units, even though it has the same unit as the label. Slightly confusing, sorry. So basically we just divide negative 1.86 off both sides. Okay, so that'll go away. We have molality all by itself, and whatever that comes out to, that's what we get. So molality for this problem is 1.61 molal. What this means is this is 1.61 moles of sodium chloride per kilogram of water. Okay? So we're going to use this piece of information as a conversion factor to solve from 50 milliliters to figure out how many grams of sodium chloride we need. Okay, so I'm going to use this as a conversion factor, so we're going to start with this. We have 50 milliliters of water. This is in kilograms, so we need to convert this to grams. The density is 1, so basically we get 1 gram per milliliter. Not a big deal. Gets us to grams, which is pretty close to what we started with. This is in kilograms, so we need this in kilograms. So there's 1,000 grams in a kilogram. Okay, and now since this isn't, we now have kilograms of water, we can use this to convert to moles. So 1.61 moles of NaCl divided by kilograms of water, which will cancel that out. We have moles and we want grams, so we use the periodic table to convert from grams to moles. Or from moles to grams, I guess. Same value we used in the last problem, it's 58.443, but this time we're multiplying. Because we need grams and we need the moles to cancel out. So we canceled out milliliters, canceled out grams, canceled out kilograms. We use this value to get from kilograms to moles, canceled out moles, and we end up with grams, and the answer is 4.7. So what this tells us is that if you had 50 milliliters of water and you added 4.70 grams of sodium chloride, the new freezing point should drop down to negative 3 degrees Celsius. Because the original freezing point was 0 and it dropped down by 3 degrees. Okay, so basically this is useful if you ever want to control the temperature of something, like to control the freezing point of it. This allows you to calculate, for a given volume, how many grams would you need. Okay, most people are kind of okay with this one. This one tends to scare them. I need you to be good at both because both come up in the real world a lot. All right, thanks.